Right. In this tutorial, we're going to do an independent samples t-test using JASP. So let's say we have a study where there is a control group and a treatment group. I'm going to go ahead and label those. So we have a control group and a treatment group. And we want to compare the control group and the treatment group for the dependent variable, the mean levels for symptom severity. So to do an independent samples t-test, we'll go to t-test, independent samples t-test, and we'll enter the grouping variable as basically the independent variable, and the dependent variable goes in the variables box, and we'll leave this alone as the straightforward student's t-test, and we'll ask for the mean difference, the confidence interval for the mean difference. The effect size we'll leave as Cohen's d, and the confidence interval for the effect size, and the descriptive statistics and the plot of the descriptive statistics. We could specify as either a non-directional two-tailed test, we'll leave it as that, or we could specify that it is a left-tailed or right-tailed test depending upon the alternative hypothesis and which mean we expected to be higher than which. But for this one, we'll just leave it alone as a two-tailed test, and just to be boring, we'll have alpha 0.05 two-tailed. Alright, so let's go ahead and look at the output. So we see that t observed is 3.14. That tells us that our mean difference is about 3 times larger than the amount of variability we would expect by chance between the means. Degrees of freedom is 18 because sample size is 20, and we have estimated 2 variances along the way, so we subtract 2, we get a degrees of freedom of 18. Our p-value is quite low, so we have a p-value, we're going to move the decimal point to the left 3 places, so that's going to be 0.005, so that's pretty low, so we're going to have, especially if 0.05 is our alpha, 0.005 is considerably below that, so we have pretty strong evidence to reject the null hypothesis here and say that the control condition has significantly greater symptom severity than the treatment condition, or in other words, the treatment leads to less symptom severity than the control group. The difference between the means is 1.9 for the dependent variable, and the standard error, the amount we would expect just by chance, is 0.6. The confidence interval for the mean difference ranges between 0.63 and 3.17. So we're not very precise in how effective the treatment might be, but we're able to rule out 0, which would be no difference in the null hypothesis. The effect size, or Cohen's d, which is the mean difference divided by the pooled standard deviation, is pretty large, 1.4. So the mean difference is 1.4 times greater than the pooled standard deviation. And the confidence interval for the Cohen's d ranges from 0.4 to 2.38. So from medium, largish to enormous. So we have evidence to suggest that there is an effect of the treatment, but we're not really sure about the strength of that effect. But we're able to rule out 0 with some confidence. All right, so we have here the descriptives, gives you the sample size per group, gives you the mean for the control group, the mean for the treatment group, and the standard deviation and standard error for each group. We can also look at a plot showing the control group and its confidence, 95% confidence interval, and the treatment group and its 95% confidence interval. So we see that the treatment is leading to less symptoms than the control. One thing that we should also look at is, although the standard deviations are reasonably similar, they're not identical, but we should check the homogeneity of variance assumption. So to do that, we go to assumption checks and click on equality of variance. And that will do the Levene's test. And we see that the p-value for the Levene's test for the homogeneity of variance assumption is quite high, which is good. It indicates that we don't seem to have a huge problem with the differences between the variances in the samples, so that we can pull the variances when we compute the pooled standard error as is done in students' t-test. If you did violate that assumption, if this p-value was very low, or the variances, which is basically this, which is the squared standard deviations, were considerably different, then you could opt instead for the Welch's t-test, which will correct for that assumption violation. All right, I thank you for listening. I hope you enjoyed that as much as I did.